Semiconductor theory. Learning objectives. At the end of this topic, you will be able to explain energy levels, discuss types of energy bands, explain different types of semiconductors, describe the concept mobility and conductivity, explain diffusion and drift current, explain generation and recombination of charges, derive the continuity equation, explain the concept of Fermi levels in semiconductors, explain the Hall effect in semiconductors. Introduction. The smallest particle of a chemical element possessing the chemical properties of an element is the atom. The first model of an atom was given by J.J. Thomson. This model explains that an atom is a sphere of positively charged matter in which electrons are surrounded. J.J. Thomson's model could not explain the features of an optical spectra of hydrogen atom and other elements. In 1911, Rutherford recognized that an atom consists of a positively charged nucleus and a number of negatively charged electrons revolving around the nucleus in orbits. The nucleus consists of a number of neutral particles called neutrons and a number of positively charged particles called protons. The charge of the nucleus is positive and equal to the number of protons contained in it. Energy levels of atoms. In the atomic structure of every isolated atom, there are specific energy levels associated with each shell and orbiting electron. The energy levels related to each shell will be different for every element. If the electron is far from the nucleus, as shown in the figure, the energy state will be higher, and any electron that has left its parent atom has a higher energy state than any electron in the atomic structure. In the figure above, the only specific energy levels for electrons in the atomic structure of an isolated atom are specified. The result is there is a series of gaps between the allowed energy levels. The energy levels of various electrons present in the first and second orbit merge to form various energy bands. Instead of the widely separated energy levels as that of the isolated atoms, the closely spaced energy levels are present in a solid known as energy bands. Covalent bond. In solids, the atoms are brought close together. The valence electrons are shared by forming a bond with the valence electrons of an adjacent atom. Such bonds are called covalent bonds. Due to covalent bonds, energy levels merge into each other, forming the energy bands. Energy bands. In any given material, bands are the most important to understand the behavior of solids. The three types of bands are valence band, conduction band, and forbidden band. Valence band. The energy band formed due to the merging of energy levels associated with the valence electrons, that is, electrons in the last shell, is called the valence band. Conduction band. The energy band formed due to the merging of energy levels associated with free electrons is called conduction band. Forbidden band. The energy gap separating the conduction band and the valence band is called the forbidden band. The graphical representation of the energy bands in a solid is called the energy band diagram. The classification of materials as insulators, semiconductors, and conductors are mainly dependent on forbidden energy gap. Insulators. In insulators, the energy gap, e.g., is large, of the order of 7 electron volt. These materials do not conduct at a very high temperature or under high voltage also. The bad conductors of electricity are plastic, glass, and wood. Semiconductor. The forbidden energy gap between the two bands is sufficiently small in case of semiconductors. Due to this small energy gap, electrons in the valence band can easily jump from valence band to conduction band if sufficient energy is supplied. As a result, semiconductors exhibit increased conductivity with increasing temperature. Also, semiconductors will have a completely filled valence band, due to which electrons are not able to facilitate conduction at low temperatures. Examples of semiconductor are germanium and silicon. Conductors. In case of conductors, there is not forbidden energy gap. It is only partially filled, permitting electrical conduction. This means that there are plenty of energy levels available for electrons to move into the conduction band. As there is no forbidden gap between valence band and conduction band, electrons can easily move from one band to another. Examples of conductors are copper, silver, and aluminium. Classification of semiconductors. Semiconductors are classified into two types: intrinsic semiconductor, extrinsic semiconductor. Again, extrinsic semiconductors are classified into N-type semiconductors, P-type semiconductors. Intrinsic semiconductors. The material which is in an extremely pure form is called intrinsic semiconductor. Germanium and silicon are intrinsic semiconductors. The process of deliberating of a very small amount of impurity into an intrinsic semiconductor to increases its conductivity is called doping, and the impurities are called dopants. A doped semiconductor is called an extrinsic semiconductor. Intrinsic semiconductor. In an intrinsic semiconductor, both holes and electrons will take part in the formation of a covalent bond. Therefore, electrons are not available for current conduction. The crystal structure of germanium and silicon materials consists of repetitive occurrence in 3 dimensions of the unit cell. Germanium has a total of 32 electrons. The covalent bonds are represented by the dotted lines encircling the 2 electrons forming the covalent bond. At room temperature, valence electrons absorb the thermal energy, due to which they break the covalent bond and drift to the conduction band. Such electrons become free to move in the crystal. Once the electrons are removed from the covalent bonds, they become free. The energy required to break a covalent bond is 0.72 electron volt for germanium. When a valence electron drifts from valence to the conduction band, breaking a covalent bond, a vacancy is created in the broken covalent bond. Such a vacancy is called a hole. Whenever an electron becomes free, the corresponding holes get generated. Hence, the free electrons are generated in pairs. The formation of an electron pair is shown corresponding to the energy band diagram. Such a generation of an electron pair due to thermal energy is called thermal generation. Extrinsic semiconductor. Intrinsic semiconductors are poor in conduction at room temperature. Hence, they are not useful in the electronic devices. Therefore, current conduction capability should be increased. This can be achieved by adding a small quantity of impurity to the intrinsic semiconductor. Hence, the intrinsic semiconductor becomes impure or an extrinsic semiconductor. This process of adding impurity is known as doping. Depending upon the type of impurity, the extrinsic semiconductors are classified into 2 types: N-type semiconductor, P-type semiconductor. Extrinsic semiconductor. N-type semiconductor. A small amount of pentavalent impurity, arsenic, is added to the pure semiconductor to get an N-type semiconductor. A germanium atom has 4 valence electrons and antimony has 5 valence electrons. Each antimony atom forms the covalent bond by surrounding 4 germanium atoms. Thus, 4 valence electrons of antimony atom form covalent bond with 4 valence electrons of an individual atom, and the fifth valence electron is left free, which is loosely bound to the antimony atom. Conduction in N-type. When voltage is applied to the N-type semiconductor, the free electrons are generated due to the added impurity and move in a direction of positive terminal of voltage applied. This constitutes the current. The holes are less in number, hence electron current is dominant over the hole current. Extrinsic semiconductor. P-type semiconductor. A small amount of trivalent impurity, boron, is added to the pure semiconductor, germanium or silicon, to get a P-type semiconductor. A germanium atom has 4 valence electrons and boron has 3 valence electrons. 3 valence electrons in boron form the covalent bond with 4 surrounding atoms of germanium, leaving 1 bond incomplete, which gives rise to a hole. Thus, a trivalent impurity, boron, when added to the intrinsic semiconductor, introduces a large number of holes in the valence band. These positively charged holes increase the conductivity of P-type semiconductor. Conduction in P-type. When a P-type semiconductor is subjected to electric field by subjecting it to a voltage, then the holes move in a valence band and are mainly responsible for the conduction. Holes are the major carriers. Mobility and conductivity. According to the electron gas theory of a metal, the electrons are in a continuous motion. The movement of electrons is being changed at each collision with the heavy ions. The average distance between collisions is called the mean free path. Since the motion is random, on an average there will be many electrons passing through the unit area in the metal in any direction at a given time. Hence, the average current is 0. Here, a constant electric field is applied to the metal. As a result of this electrostatic force, the electrons would be accelerated and the velocity would increase indefinitely with time, where it is not for the collisions with ions. At each inelastic collision with an ion, electron loss energy and a steady state condition is reached, where a finite value of drift speed is attained. The drift speed is in the direction opposite to that of the electric field, and its magnitude is proportional to the constant electric field. Thus, V is equal to mu epsilon, where mu square meter per volt second is called mobility of the electrons. Conductivity. According to the foregoing theory, a steady state drift speed has been superimposed upon the random thermal motion of the electrons, such that the directed flow of electrons set up a current. If the concentration of free electrons is N, which is electrons per cubic meter, the current density J, which is amperes per square meter, is Rho is the conductivity of the metal. Diffusion current. Consider a piece of semiconductor which is non-uniformly doped. The charge carriers are either electrons or holes of one type depending on the impurity used. They have the same polarity and hence experience a force of repulsion between them. The result is that the charge carriers start to diffusion from a region of high carrier density to the low carrier density. The diffusion current continues till all the carriers are evenly distributed throughout the material. Charge carriers start to diffuse from region of high carrier density to the low carrier density. This movement of charge carriers under the process of diffusion constitutes a current called diffusion current. Diffusion current density due to holes is given by, since the hole density decreases with increasing x, dp by dx is negative and the minus sign in the above equation is needed in order that Jr has a positive sign in the positive x direction. Diffusion current density due to the free electrons Jn is given by, where dn by dx and dP by dx are the concentration gradients for electrons and holes respectively in the x direction. dN and dP are the diffusion coefficients expressed in centimeter square per second for electrons and holes respectively. Drift current. If a voltage is applied to a semiconductor, the free electrons move towards the positive terminal of the battery. The electrons moving from the positive terminal collide with the atoms of semiconductors and connecting wires along its way. Each time the electron strikes an atom, it rebounds in a random direction. The applied voltage makes the electrons drift towards the positive terminal. This drift causes the current to flow in a semiconductor under the influence of applied voltage. This current produced due to drifting of free electrons is called drift current. The drift current means the flow of current due to bouncing of electrons from one atom to another, traveling from the negative to the positive terminal of the applied voltage. Generation and recombination of charges. When a bond is incomplete, the hole exists. It is relatively easy for a valence electron in a neighboring atom to leave its covalent bond to fill this hole. An electron moving from a bond to fill holes leaves a hole in its initial position. Hence, the hole moves in the direction opposite to that of the electron. This hole in its new position is now filled by an electron from another covalent bond, and the hole will correspondingly move one more step in the direction opposite to the motion of the electron as shown in the figure 1. The mechanism for the conduction of electricity takes place, which does not involve free electrons. Generation and recombination of charges phenomenon is illustrated mathematically in figure 2. The complete circle with a dot represents a complete bond and an empty circle represents a hole. In the figure 2a, the row of 10 ions can be seen where the broken bond or hole is present at ion 6. Imaging if the electron from the ion 7 moves into the hole at ion 6, the configuration of figure 2b results. By comparing both the figures 2a and b, it looks as the hole in figure 2a has moved towards the right as shown in the figure 2b. The motion of hole in one direction actually means the transport of a negative charge at an equal distance in the opposite direction. The continuity equation. The continuity equation is based upon the fact that charge can be either created or destroyed. Consider the infinitesimal element of the volume of area A and length dx within which the average hole concentration is P. If tau P is mean lifetime of the holes, then P by tau P equals holes per second lost by recombination of per unit volume. If E is the electronic charge, then because of recombination, the number of coulombs per second decreases within the volume is given as. If G is a thermal rate of generation of whole electron pairs per unit volume, the number of coulombs per second increases with the volume is given as. In general, current will vary with the distance within the semiconductor. From the figure, the current entering the volume at x is I and leaving at x plus dx is I plus di. The number of coulombs per second decreases within the volume is equal to di. Due to the three effects enumerated, the hole density must change with time and the total number of coulombs per second increases within the volume is given as. Since charge must be conserved, the whole current is sum of diffusion current and drift current. If the semiconductor is in thermal equilibrium with its surroundings and is subjected to no applied fields, the hole density will attain constant value. Under these conditions, the above equation indicates the rate at which holes are generated thermally equals the rate at which the holes are lost because of recombination under equilibrium condition. Combining equations 5, 6 and 7, we get the equation of conservation of charge or the continuity equation as injected minority, a carrier charge. Thermal equilibrium hole concentration in N side plus injected hole concentration in N side is given as, where Lp is the diffusion length for holes in the N material, V0 is a barrier potential, Vt is a volt temperature equivalent. At room temperature T is equal to 300 Kelvin and Vt is equal to 0.026 volts. According to Boltzmann relationship of kinetic gas theory, in the case of open-circuited p-n junction, it is given as, in the case of p-n junction, forward biased by an applied voltage V at X is equal to 0. Comparing equations 1 and 2, we get, this boundary condition is a law of junction. Law of junction. If the hole concentration at the edges of the space charge region are Pp and Pn in the P and N materials, respectively, and if the barrier potential across this depletion layer is Vb, then this is the Boltzmann relationship of kinetic energy theory. It is valid even under non-equilibrium conditions as long as the net hole current is small compared to the diffusion or the drift hole current. This condition is called low-level junction. To get the approximate values, the magnitudes of the diffusion and drift currents are equated. If the equation 1 is applied to the case of an open-circuited p-n junction, then hole concentration in P side is equal to thermal equilibrium hole concentration in P side. Hole concentration in N side is equal to thermal equilibrium hole concentration in N side, and Vb is equal to V0. By substituting these values in equation 1, we get, from the above equation, we obtain the contact potential. Consider now a junction biased in the forward direction by an applied voltage V. Then the barrier voltage Vb is decreased from its equilibrium value V, not by the amount V. The hole concentration throughout the P region is constant and equal to the thermal equilibrium value, or hole concentration in P side is equal to thermal equilibrium hole concentration in P side. At the edge of the depletion layer, X is equal to 0, hole concentration in P side is equal to thermal equilibrium hole concentration in P side. Combining equation 3 with equation 2, we get, this boundary condition is called the law of the junction. It indicates that forward bias, the hole concentration at the junction is greater than the thermal equilibrium value. Fermi level in intrinsic. Fermi level lies in the center of forbidden energy gap for intrinsic semiconductor. Fermi level is given as, where EF is Fermi level, EC is conduction band energy level, EV is valence band energy level. Fermi level in N and P-type semiconductors. In N-type material, Fermi levels are just below the conduction band. Fermi level is given as, in P-type material, Fermi level is just above the valence band. Fermi-Dirac function. The distribution function that explains the distribution of energies among different electrons within a crystal at a given temperature is developed by Fermi and Dirac. This is called Fermi-Dirac energy distribution function. This function allows to find the number of free electrons Dn per unit volume which may possess a value of energy in range E to E plus dE at a given temperature T. The number of free electrons Dn per unit volume, which may occupy energy level between E to E plus dE, is given by the density distribution function is expressed as where Ne is equal to density of states in the conduction band and Fe is equal to probability that the quantum state with energy E is occupied by an electron. The probability function Fe is called Fermi-Dirac probability function. In a semiconductor, the lowest energy level in the conduction band is E. The Ne is given by the gamma is proportionality constant and given by where m is equal to mass of an electron, q is equal to charge on electron, h is equal to Planck's constant. From the principle of quantum mechanics, the Fermi-Dirac probability function is given by where k is equal to Boltzmann's constant, T is equal to temperature, Ef is equal to Fermi level or characteristic energy for the crystal in electron volt. E is equal to energy level occupied by an electron. Hall effect. If a specimen of metal or semiconductor carrying current I is placed in a transverse magnetic field with flux density B, then an electric field E is induced in the direction perpendicular to both I and B. This phenomenon is called Hall effect. Consider a semiconductor strip carrying current I as shown in the figure. The current I is flowing in positive x direction. It is placed in the magnetic field with density B action in positive z direction. In such conditions, the force is exerted on the current carriers in the negative y direction. This force is called Lorentz force. Thus, if the semiconductor used in N-type, all the electrons which are majority carriers will be forced towards side 1 of the strip. Hence, side 1 will become negatively charged with respect to side 2. Thus, there exists a potential difference across the sides 1 and 2. This voltage is called Hall voltage, denoted as Vh. In the equilibrium condition, the electric field intensity due to the Hall effect must exert a force on the carrier which just balances the force exerted by the magnetic field, where E is equal to magnitude of charge on the carrier, V is equal to drift speed. Now epsilon is given as where d is equal to distance between the surfaces 1 and 2, the current density J is given by, while the current density can be expressed in terms of charge density as, where rho is equal to charge density in coulombs per second, V is equal to speed in meter per second, W is equal to width of the strip in the direction of B, equating 3 and 4 we get. If the polarity of VH is positive at terminal 2, the semiconductor must be p-type and charge density is equal to Ne, where N is the electron concentration. If the terminal 1 becomes charged positively with respect to terminal 2, the semiconductor must be p-type and charge density is Pe, where P is the Hall concentration. The Hall coefficient RH can be defined as, if the conduction is due primarily to charges of one sign, the conductivity is related to the mobility by the below equation. If the conductivity is measured together with the Hall coefficient, the mobility can be determined from the equation below. Applications of Hall effect. Hall probes are often used as magnetometers. Magnetometers are used to measure magnetic fields or inspect materials such as tubing or pipelines using the principles of magnetic flux leakage. Hall effect devices produce a very low signal level and thus require amplification. For determination of p-type or n-type carrier concentration, the mobility can also be calculated with simultaneous measurement of the conductivity. The conductivity and the mobility are related by the equation. Numerical. A particular diode carries a forward current of 60 milliamperes when a forward voltage of 0.2 volts is applied. Find the DC forward resistance. It carries a reverse current of 25 microamps when reverse voltage of 60 volts is there. Find its DC reverse resistance. Numerical. The mobility of free electrons and holes in pure germanium are 3800 and 1800 centimeters square per volt second respectively. The corresponding values for pure silicon are 1300 and 500 centimeters square per volt second respectively. Determine the values of intrinsic conductivity. N phi is equal to 2.5 into 10 to the power 13 for germanium, and N phi is equal to 1.5 into 10 to the power of 10 for silicon at room temperature. Summary. At the end of this topic, you have understood the structure of an atom, energy levels, types of energy bands, the types of semiconductors, the concept of mobility and conductivity, diffusion and drift currents, generation and recombination of charges, the continuity equation, the concept of Fermi levels in semiconductors, the Hall effect in semiconductors.